Hello everyone. Today we would like to talk to you about Sing, our new method to analyze invariants in classifiers. As most of you know, classifiers are many to one black boxes, where several inputs can lead to the same output. Most of the time, we expect that only semantic similar inputs will have the same output, as non-informative features should be ignored. But in on rare occasions, this is not the case, and we usually cannot explain why. Many algorithms exist to explain and interpret neural networks. Some of them are model agnostic, and some of them are model specific. Nevertheless, all of these methods have difficulties to explain what a model ignores. Recent work, such as text-to-concept, are using multimodal vision language models, such as CLIP, to attach a semantic meaning to vision model features by translating features from a classifier space to CLIP space and scoring it to a concept text embeddings. This approach doesn't explain as well what the model ignores, but our story starts from here. Sing, or semantic interpretation of the null space geometry, consists of 4 steps. In the following slides, we're going to dive deeper to each of those steps. In step A, we extract the classifier head of the model, which is usually a linear head, and break it with the SVD into 2 projection matrices, principal and null. In step B, we take another set of images, such as ImageNet, and create 2 types of datasets, one of features from the classifier head and one of features of CLIP. Then we train a translator that translates from the classifier head space to CLIP space. In step C, we create equivalent sets, which is a set of different features that lead to the same output in the classifier head. For example, null removal. Then, in step D, we analyze equivalent pairs in 2 methods. One is scoring with text, same as previous methods. 2, by feeding them to unclip in order to generate meaningful semantic images, trying to capture what a single prompt can't. We introduced 2 new metrics based on the well-known CLIP score, and it is most intuitive to think about them as angles. While CLIP score measures the angle between an image and text embedding, image score measures the difference in angle between 2 images, describing visual changes. And the attribute score measures the textual or perceptual drift between 2 images against a certain text. For example, starting with the shark image. More image score, different image. More attribute score, different shark. As stated before, we took ImageNet with 1000 classes and 13 pre-trained classifiers, and for each of them we trained a linear translator from their penultimate layer to CLIP L14. Now we are trying to ask, what is an ideal null space? We assume that an ideal null space should hold no classification relevant information, suppress irrelevant noise, and maximize separability. For example, if we remove the null space from an image classified as class 1 with large IS and no AS, we will see large changes in semantics that are not class 1 informative. Hence, we took a set of null-removed equivalent features and measured the ratio of IS to AS. Again, large ratio is the wanted case, as it projects to a large null space with no class-specific information. Here we can see the 2 cases when we remove the null space. On the left side, we see in the yacht that if we remove the null space, we still see the yacht. The changes are mostly semantics and non-class informative. While on the right side, we can see a chimpanzee that once we remove the null space, it changes the semantics drastically in a class informative way. Here are some null removal results over starfish images. The first row represents the original feature, while the equivalent is after the null removal. We can see on the left side that the Dinovit is the most stable one across the 4 models we chose. And here are for chimpanzees. We can see in both cases that Dino was the most stable one. In this example, instead of removing the null space, we partook to attribute directions in the null space, or specifically to the brown attribute. Again, we can see how Dino remains more stable than the rest of the classifiers. And here is another case with big null perturbation, where ResNet on the middle right column is more stable than Dino. What is important to note in all of those examples is that Sing can actually quantify and score those cases, what we couldn't do with previous methods. In our final experiments, we saw that class perturbations can completely change the features to different classes. This can highlight vulnerabilities in vision classifiers and how the null space can be used to trick them. Thank you so much for listening and have a good one.